Hi, my name is Mike. Today I'm going to be talking about a liquid crystal. Before we begin, I'd like to let you know that this is by no means a detailed explanation on liquid crystal. So without further ado, let's just begin. Okay, so when we're talking about liquid crystal, we have to talk about the general state of matter. Well, generally we know that there are liquid, solid, and gas. So what makes them so different? So, well, if we look at the molecular level, or this is just a representation of it. So let's say I have I have an atom over here and solid crystal. The molecules in crystals they exhibit both positional and directional order. Let me write it over here. So what we are going to observe is the positional order and orientation or directional order. So this is just a simple yes or no kind of situation. Oh, well, let's see the first case here. This is a solid crystal. So, like I said earlier, that molecules in a crystal, they have both positional and oriental order. What does that mean is, well, if you look at the atoms over here, they kinda facing at the same direction, whether you like it over here or here. But the thing is, they all of the atoms here in certain area of my material here, they are all of the atoms, they are facing the same direction. So I will say that solid crystal they have orientation order. And how about positional? Well, we can look again that each of these crystals they are having the same structures, or each of these atoms have the same distance to each other with respect to each other. So of course, then they do have positional order. Then let's look at plastic crystal over here. They have the same sort of orientation, or I should say positional, sorry. They have the same positional order over here, like with respect to each other. So this atom and this atom and this atom, they are separated by the same certain distance, let's say A. But they don't necessarily have the same orientation. As you can see, uh, let's say this atom, the is facing that direction or this direction, and the other atoms is facing on the opposite direction. Right. So plastic crystals, they do have positional order, but not necessarily an orientation order. Okay, let's jump into liquid first, shall we? An isotropic liquid. Okay, let's see here. They do have, oh no, actually they don't have. They don't have both positional order, like you can see here. They are not really in ordered structures. One atom with each other atoms, and the orientation they don't have the same orientation. So no. And now we can go to liquid crystal. Liquid crystals. What's so special about them? Okay, well, first we are going to analyze this first. If we look at this structure here, well, what can we deduce from it? Well, liquid crystals, they do have the the orientation of all the atoms in here in the same direction, whether it's up or down. Uh, the atoms they have the same direction facing, but they don't have the positional order. I mean, this picture don't really emphasize it, but liquid crystals don't really have a positional order. So this way. So let me break that again. Well, molecules in crystals, they both possess positional and orientational order, which keeps the molecules constrained to one point, or constrained to point in one certain direction, and to be in one certain position with respect to each other. While in liquids, the molecules do not have any positional or directional order, so the direction of the molecules pointing and positions, well, they are not in order or completely random. So that's why we call them isotropic. Or in other words, we know them as the mesomorphous mesomorphous state. Now I'm going to introduce you to um, a tools or a method, other method to know which state that a material is in. It is called a DSC. DSC. Uh, it's short for differential scanning. Oops, sorry about that. Calorimetry. So what they basically do is we are measuring what is the heat flow required to keep the material at a certain temperature. So the graph will look like this. Oops, my bad. I'm going to draw a nicer graph over here. So this is the heat flow. Heat flow and as a function of temperature. So standard materials like let's say solids, they will form a graph like this. And at this point, at the peak, I'm going to say somewhere around 145 degrees Celsius. And at this point, the materials, at this point, we don't know what it's called, right? I'm just going to call it a certain material, which exhibit both liquid and crystal properties. Well, at this point, the materials they look kind of hazy at first, like a hazy sort of, and it flows. So we heat them to a certain temperature, and it reaches a certain heat flow. Then we observe what kind of properties it has, and if we heat them again, it will just make it like this, right? So this is the solid phase, and this is around 172 degrees Celsius. Well, at this point, what becomes of the material? Well, it became transparent. It becomes liquid. So what we can say about this is liquid crystals, okay, this is solid. This is the solid area, and in here uh, we kind of reach the liquid phase. I already wrote that. Okay, and this area in between, well, this is the liquid crystals. So macroscopically, they looks like liquid, but if we look at them even further microscopically, this liquid, or I should say liquid crystal, they possess some order of the crystal properties, like the optical properties of crystals. So I'm just going to write this again. Microscopically, they look like liquid in this area over here, but microscopically they possess some of the characteristic that crystals have. Right. So this is what we call the liquid crystals. And the liquid crystals, the phase, they exist between the solid and the liquid phase. Uh, okay, when we look in the molecular level again, the molecules in a liquid crystal, like I said before, they don't exhibit any positional order, but they do possess a certain degrees of orientational order. So the molecules don't all point the same direction all the time at these liquid crystals. But when we're talking about these molecules, what are we really talking about? What are the building blocks of liquid crystals? I'm just going to short it for LCs, for liquid crystals. So basically they are molecules, but in the field of liquid crystal, we call them mesogens. Since mesogens, they're still molecule, so their characteristics or shapes, they're still governed by the shape of the molecules. So for example, there are two most well-known mesogens. We call them the calamitic mesogens, or the fancy word for it is, oh sorry, this is the fancy word. Uh, the most common word is, this is the rod-like mesogens. So they're actually molecules with hydrocarbon chains and all that, but we're not going to talk about them in here. So I'm just going to symbolically draw them like this, like long rod shape, like this. Okay, that may not be the best drawing ever, but you get the point. So one of the building blocks of liquid crystal is just like this. But well, yes, of course, it's not just these messages alone. In this type of or calamitic like, or sorry, rod like messages, they tend to align with each other. So you're going to have another calamitic messages in or this ordered fashion like this. And we move to the other one. It's called a discotic messages. As you might have guessed, this is a disc-like structure over here. They're actually a three-dimensional beings, or yes, something like that. This is also, but what differs them is that, so I'm going to call them, they have a certain length, L, and a diameter. So in calorimetric messages, the length of the messages is obviously larger than its diameter, hence why the shape is like a rod-like. While in the discotic messages, they are obviously the diameter is obviously larger than its length. So this is supposed to be like this. And the discotic, rather than aligning itself with another discotic messages, well, they do align actually, but they are more like stacked on top each other. So it's more like this. This is another disk-like messages on top of each other. Again, I'm sorry for my drawing, but okay, I hope I get the point across. Right, so this is uh, the simple explanation on what is the building blocks of liquid crystals. But okay, the next is where do we usually find liquid crystals? Well, we actually do have them in our bodies. In living systems, they are called the iotropic. They are they are found in proteins. So they're basically nature made LC, like something like that. Proteins, cell membranes, etc. And the other big group is called thermotropic liquid crystals. And this is what mainly what we are going to discuss in this video. So we got the nematics, smectic, and cholesteric. Alright, before I go into further detail of these three, uh, I'm going to explain them in simple words. So, the nematics liquid crystal, they are what we usually found in uh, LCDs, something like LCDs like that. So in display technology. So the point is they can be the orientation and positional order of the messages, the calamitic one. They can be aligned or manipulated by electric field. And the smectic one, well, they form layers, as we will see uh, next later in the videos. They will form something like this. Yeah, so this is actually this is the messages making up of the liquid crystals and the cholesteric. Cholesteric, or in other words known as twisted nematics. You will see why later in the video. Right, so this is the general overview of liquid crystals so far. And well, what's so special about liquid crystals? What makes it differs uh, from ordinary, from general crystal or liquid? Well, liquid crystals, they have these special effects on polarized light. So they actually change the polarization of light. So light, as you know, is an electromagnetic field. I'm going to draw it like this. Right, so I'm just going to draw this axis here. This is the the plane. This is the XY plane. Right, so the light they propagate, and we do have this some kind of polarizer. I'm going to make it like a slit like this. So what this polarizer do? They filter out, or they polarize the light that came into it and change the polarization of the light. So yeah, that's obvious. But so they only let the light pass if they have the same polarization as this polarizer. So if they came out like this, they will filter out any. Um, let's say this is a horizontal polarizer. So they will filter out any of the light that vertically polarized. So what came out of this is also a horizontally polarized light. Like this. The same thing will happen if we let this polarized light into another polarizer, but this time I'm going to make it vertically polarized. What will happen is there will be no light at all that um, our eyes would see. This is our eyes. Sorry, man, our eyes has hair on it, so there will be no light at all. But if we place, a liquid crystal in between this polarizer, let's say I have this really thin liquid crystal, then these liquid crystals will change the polarization of the light propagating through it. So when we place these liquid crystals in between these two polarizers, these two perpendicular polarizer, then light will actually pass through the second polarizer, and our eyes will see that uh, our eyes will be able to see the light coming through. So, so that is what's so special about liquid crystals. Solids don't do this. An isotropic liquid don't do this. So liquid crystals, they do. So uh, I was talking about earlier. I was talking about the structures of the liquid crystals, and one thing that we would like to know is how ordered are the liquid crystals? Like how ordered? say if I have a bunch of messages like this, oops, like this, how do we say um, both qualitatively and quantitatively they are ordered? So I would like to introduce in 2 dimensions. Um, sorry, let's rewind that back. So in liquid crystals, we have this term called descriptors. It basically describes the structures of liquid crystals and what differentiate between nematics from smectic, smectic from uh, chiral, liquid crystal, etc. So descriptors, we would like to know them. And this could be a quantitative measurement. So in general, well, if you look at this, messages that I have drawn over here, well, we will say that the average orientation of the liquid crystal is this way. All right. Yeah. So the average, the average direction of the messages are pointing at is called, uh, well, we will call it director. So this is the average. This is the average direction of the messages are pointing at, and each messages may be different from other messages. So if I draw it like here, I'm just going to a simple drawing here. Oops, I'm going to delete that and this too. Descriptor. This is the director. I'm going to call it with. I'm going to denote it with factor n, the unit factor n. So in general, we have these two descriptors. They are called S and sigma, as we will use them on nematic structures, and they are called the orientational order parameters. And the sigma is a translational order parameters. Right, so first we would like to discuss about this, the S parameters. For simplicity and etc., I'm going to draw it in 2 dimensions first. So let's say I have the director pointing up like this, And these messages, this one certain messages pointing at direction pi. This is of unit vector 2. Right. I'm going to make it a little bit nicer right here. So I have this director and this particular pneumatics messages pointing this way, and the angle between them, let's call that a theta I. So the other parameter s is actually defined as 2 times the expectation value of n hat times pi hat. So this is a factor product of n and p, sorry, over all of the volume. So I have these messages over a certain volume v, this, and each messages, they have their own orientation at certain angles with respect to the director. And I would like to know what's the expectation value of this product over all the volume. Minus 1. Okay, this is the full equation right here. So we would like to solve this first. So, well, as you know, this is just a simple dot product. So it will equal to the magnitude of the director times the magnitude of that certain messages times the cosine of the angle between them. And since this is a unit vector, oh, sorry about that, then this 2 actually has the value of 1. So it will be just cosine of theta I. So we write them again here as it's equal to cosine squared, forget about the square, of theta over all the volume minus 1. But then again, how do we determine this cosine squared theta? Well, this is not just we are looking for the value of the cosine, but this is the probability that a certain molecule has an orientation of theta. So this is actually, if you write it like this, it will be equal to cosine squared theta times this is the probability of finding theta. Right, let me correct that. Actually, this cosine contains the probability of theta over all available angle. And then we normalize it. We normalize it. P of the probability again, like that. So we know that this term is the probability, but what does it look like? So what is it actually? Well, if we'll draw it in a graph, this is theta, then the probability will look like this over all theta. Of course, this is if you zoom in like this, it will look like this, but it's actually much narrower than it seems. So like uh, maybe like this, or maybe even more or less. So this peak and this probability is uh, actually correspond to the angle where the director is pointing at. So most of the molecules have the orientation of the director, but qualitatively speaking, how well they are ordered is simply by uh, looking at this width. So how well they are ordered is described by the width of the peak. So the width of this from here to here indicates how ordered the molecules are aligned or pointing at. Okay, so let's continue. So we already talked about this probability. Um, okay, earlier I said that uh, liquid crystals are an intermediate place between a crystal and a liquid. So let's just ask the question here. What is the probability of theta in solids on crystal? Well, it's either 0 or 1. 0 for theta not equals to 0. So the probability will be 0, and the probability will be 1 for theta equals 0. Oh, sorry about that. I wrote theta. So what does this mean is uh, 0 actually is the angle of which the director is pointing at. So I will say like this. In solids, they are pointing at the same orientation. This is the 0 degrees, and the probability of finding another uh, theta not equals to 0 is actually 0. So for solid, it is 1. And it implies that the cosine or the average cosine theta is equal to 1. And if you plug it in into the S equation above, it will be 2 times 1 minus 1, and that will be equal to 1. Okay, so this is the orientation order parameter for crystal. But how about a completely isotropic liquid? So this is for crystal, for solid, right? And let's continue that for liquid. In liquid, the probability, well, it will be constant because the probability of finding theta must be equal for all of the messages pointing at. So they're completely random, so they are constant. So this is equal some constant. So I'm going to delete that. Oops, my bad. This is equal some constant. So the cosine squared, the expectation value of this over all the volume is well, let's write that equation once more again. This is cosine squared theta, and this is the probability of theta over all angle. And then we normalize it. But since this probability is constant, we treat them as a constant, so we just get them out of the integral, and bye-bye. We will be left with pi. We integrate from 0 to pi for cosine squared theta over all theta. Like this. Right, so we have gotten this far. What is we're going to solve for we're searching for S, right? We're searching for S. Then we have to know this value actually. Okay, let's start with the cosine squared. So this is just math. I'm going to explain, not into the physics of it, just math. So the cosine squared, actually I've done the math, but I'm short on time, so I'm just going to skip it, and this is actually half pi over integral of d theta is just over 2 pi is just pi, and we found that the cosine is just 1/2. So we plug it in again. You plug it in into this equation. -1. Well, this is 0. Notice that for crystals, that the value is 1. The order parameter is 1. While in liquid, it's 0. So if I were to make an upper and lower limit, this will be 1 and 0. 1 for crystals, and 0 is for liquid. And if you already guessed that liquid crystal is actually one bit, it's actually in between these two values. So it will be, well, the value has been found, but I'm not going to derive it in here. So I will just say that for liquid crystal is from 1.3 to zero point 0.7 for liquid crystals, but anything in between is actually considered to be liquid crystals. So this order parameter S is actually tells us um, how the material, whether the material is liquid, solid, or in between. So the if you look in here again, the director itself is a descriptor, but it doesn't tell us what what the base of the matter is. Is it liquid or solid or in between? But with the S parameter, we can actually tell the orientation and the phase of the matter. Okay, so uh, this is true for nematics and smectic. Well, actually, it's a little bit different with smectic, but it's generally the same. Well, now, how about I'm going to move to a whole different slide over here. Well, how about the cholesteric one? Cholesteric LC. Well, as the name suggests, it is actually made from cholesterol. But uh, the director, well, if the nematics have a certain director, like pointing at some direction here, or upward, downward, to the left, or anywhere really, the cholesteric LCs, liquid crystals, they have these helical structures of director. Okay, I'm going to write draw it better. Okay, so here, ooh, awful. So this will be the direction of the director is pointing. So this is a helix or helical director. And the most important variable of this helical director controlling the optical properties and color of which the light passes through it is called the pitch. It is actually the distance, the vertical distance of uh, one to traverse one rotation of the helix. This is the pitch. So this is what determines how the light is transmitted uh, through the cholesteric liquid crystals. So this is actually, or director in general. Well, they dictates the optical properties of the liquid crystal, like that. So, and in this case, the longer the pitch, I should say this, the longer the wavelength is reflected. So if I say this is some wavelength of lambda, I'm just going to draw it like I over here, and this is um, the size of the pitch, and it would be it corresponds to larger wavelength and larger pitch. So the longer the pitch, the longer the wavelength, and the more apparent the color. So if you are passing a pale blue light through these cholesteric liquid crystals, then uh, the light coming out of this will be more blue in color. So the pitch is actually to the wavelength.